Welcome back to another week of physics. Okay, so before I start, again, please sign in below. Helps me out. Helps my bosses know what's going on. And, comment on the video if you have any questions. And I'll try to get back to them. I'm trying to look at, the videos once a week to see if there's, or a couple times a week to see if there's questions. Haven't seen any yet, but anyways. So number one. So we're going over rotational motion this week. So number one, a disk spins at a constant angular velocity of 31.4 radians per second. What is the tangential velocity and net acceleration of a point 0.5 meters from the center of the disk? Okay, so let's draw out what we got going on here. So we got a disk. Okay, so we got a disk, center of disk right here. And then we have some point that's probably, let's say it's right here. It's 0.5 away from the center of the disk. So this distance right here is 0.5 meters, okay? So what's going on? So it has an angular velocity, which is dark. Okay, so it has angular velocity. It gives us the angular velocity. It wants to find the tangential velocity and the net acceleration. Okay, so angular velocity, what is the relationship between angular velocity and tangential velocity? Well, we know this equation, right? So V tan equals angular velocity times the radius, right? So that could easily get us the tangential velocity. So how do we do that? Just plug in our numbers. So the angular velocity is 3.14 radians per second. And then the radius is just, so it's times 0.5 meters, and I'll say per radiant. Okay. And I say per radiant because essentially 1 radiant of the circle, it equals like an arc length of 0.5 meters. So you don't have to put radians. But anyways, it cancels, it makes the units work, right? So cancel the radians, now we have meters per second. So the tangential velocity equals half of that. So look at my notes, 15.7 meters per second. That's the tangential velocity, right? So tangential velocity is just going tangent to the circular path that's going on, right? Yes. And we know that the velocity is pointing in that direction because our angular velocity is positive, right? So we have a positive angular velocity, and we know that when it's positive, the disk or whatever the object is spinning counterclockwise. Yeah, I'll try to explain that. There you go, I'll explain it now. So angular velocity, and this is similar with like torque and stuff. So they say like counterclockwise is positive. I usually think of it as like, oh, it's the unit circle. So think of a circle as a unit circle, right? If you were to trace like in a positive, so like this is 0, this is pi, right, and 2 pi, whatever. This is pi over 2. So when you're going counterclockwise, you're tracing the unit circle in the positive direction, right? So you're getting a positive angle. When you go counter, or when you go clockwise, then you're going in the negative direction on the unit circle. So that's how I think of it. I don't know 100% if that's correct. I think it is, but anyways, that's how I do it. So net acceleration, right? So we want to find net acceleration here. Let me erase this extra stuff. I want to write on it. Okay, so net acceleration of this guy right here. So what is the net acceleration? Well, net acceleration, right? That's a combination of all the whatever accelerations that's going on. So we have two things. We have a tangential acceleration, and we have the what's called like the angular acceleration. Yes. So the tangential acceleration, right? It's just like this, right? So this is a tan, and then the radial acceleration is just going towards the center, right? So it's like the centripetal acceleration, right? Going towards the center. So we want to find the net acceleration. So it's a combination of these two. So essentially we're going to be like adding these two together to get the net acceleration, which is that, right? So how do we add these two together? Well, what we could do is sort of make this thing a triangle, right? I don't know how to like pick up lines and move them. But like if I were to take this line right here, right, move it over here, right, add them together, it should equal, it should go tip to tip with that line. So then we know, or we'll be able to find out the angular, the tangential acceleration and the angular acceleration. We know how to get those two values. And then we could just do Pythagorean's theorem to find the third side of the triangle, right? So essentially, when we put it all down, it's the net acceleration equals the square root of what is it? A, so angular acceleration plus tangential acceleration squared. Okay. So yeah, let's do this. Let's find these two accelerations. So how do we do that? Well, for the angular acceleration, we have this cool equation that is AR equals W squared times R. All right, so the angular acceleration here equals 31.4 squared times 0.5. So that is 492.98 meters per second squared. And then what is the tangential acceleration? Well, let's look. It says a constant angular velocity. All right, so back to week 1 when we talked about what constant velocity meant. If it's constant velocity, then the tangential velocity is going to be 0. Okay, so tangential velocity is 0, angular velocity is 400, and that. Then we plug it in. That equals square root of 492.98 squared, right? And then you square root of square, that cancels out. So A net equals 492.98 units. Okay. Yeah, that's the answer right there. So we got our net acceleration and our tangential velocity. Okay. All right, let's do it. So number 2, the wheel of the car spins at 30 revolutions per minute for 5 minutes. The diameter of the wheel is 1 meter. What is the angular speed of the wheel in radians per second? What is the angular displacement of the wheel during this time period? And how far does the car travel in 5 minutes? All right, let's break this up and do separate questions. So this is part A. So what is the angular speed? Part B is the angular displacement. Part C is how far does the car travel? So part A. So we're given a speed, right? So the car's wheel spins at 30 revolutions per minute. And then we want it to get to angular speed. So what is the units of angular speed? Well, it's radians per second. So we want it to get to radians per second. How do we do that? Well, we could do sort of this unit conversion thing, right? So we know that one revolution around a unit circle is 2 pi radians. Okay, and then we know there is 60 seconds and 1 minute. Nope, seconds. So then it cancels out everything, right? that gives us 3.14 radians per second. So that's perfect. That gives us our angular velocity, right? 3.14 rad per second. Awesome. That's part A. So part B, what is the angular displacement of the wheel during this time period? Okay, angular displacement. So angular displacement, we got a little equation, equals angular velocity times time, right? And it makes sense with the units, right? So if we plug in our angular displacement, so 3.14, I'll put the units in, just to make sense, times time. So now we have to convert our time, so 5 minutes into seconds. So when you do that, it's just 300 seconds times 300 seconds. Seconds cancel out, and now we got the angular displacement of 942 radians. Okay, so that is our angular displacement, 942 radians. C, part C. So how far does the car now travel? All right. So now that we have the angular displacement, we want to see essentially how far it travels. So we have this little equation, S equals angular displacement times the radius of the wheel. So then we plug in our variables, so 942 radians times 0.5 meters per radian. Then we get a distance of 471 meters that this car traveled. Okay, so essentially that wheel, right, if you sort of do like on a unit circle, like the radians or whatever, it traveled 962 radians, right? I think there's around like 6 radians in one cycle or so, right? 2 pi. 2 pi is one cycle, so it's around 6. So that's a lot of, radians, a lot of cycles of that wheel, and then when you convert that to like meters, essentially, that's what you get. Cool. That's number 2. Let me stop this recording. Okay, so net torque. What's the net torque on this bar, and which direction is it rotating? Cool, so we have 3 forces on this bar, right? And sort of this pivot point right here. So we got 3 forces and a pivot point. I'm gonna do it in brown because there's a lot of colors. Okay, so we got 1 force. So the first force going up, second force going down on this side, third force going up on that side. So what is the equation for net torque? So essentially, we have to add up all the individual torques that these forces are applying here. So, right, so torque 1 plus torque 2 plus torque 3, essentially, right? And then how do I get the torque for the first force? So equations, right, easy equations. So it's force times the radius. So torque equals like the force, or we'll say radius times force. I think it should be on the equation sheet. So radius times force. And these forces are perfect, right? They're perpendicular to the plane of surface that they are pushing against. So all of that force is being applied directly in that direction onto that, on that thing, whatever that thing, the bar. Okay. So, yeah, let's do it. So the tricky thing here is defining what the positive and negative direction is. So this thing is going to be spinning in a circle, right? Blue, I haven't used blue. So it's going to be spinning either this way, right, or the opposite way, right? So this way. So we have to define what is going to be positive and what's going to be negative here. Okay, so I think it's easiest always, and Professor said this, you want to define counterclockwise as positive, and how I sort of explained it before, as you're going to be tracing positively along the unit circle, right? If you imagine the circle as the unit circle, the circular motion is this unit circle, and it's going to be tracing positively around the unit circle, and then the opposite way, or clockwise, will be tracing negatively. So that's how I would define it. So the first force is pushing in the positive direction on the unit circle, so we'll say that's a positive force. So it's 200 newtons times 3 meters, right? Because it's 3 meters away from the center that is rotating. And then the second one over here, 100 newtons, and it is pointing in the positive direction, right? Because it's going to make that circle go counterclockwise, which we define as a positive direction. And it's 4 meters away. And then the third force is pushing in the clockwise direction, right? The opposite direction. So it's going to be negative. It's going to have negative torque, right? So 300 times 2.5. Cool. So those are all the individual equations for torque. So when you add all that up and do all the simple math, you get a torque of 250 Newton meters, right? And it's a positive torque. So what does that mean? Positive torque, it's going in the counterclockwise direction. That's how we defined our positive and negative like axes, right? So counterclockwise direction. Okay. Yeah, let's just go on to 4. I need to stop this. What is the net torque on this wheel, and which direction is it rotating? Okay, so similar thing. We have to define what is positive, negative direction. It's best to define it as counterclockwise being positive and clockwise being negative. So, and it's going to be the same thing, right? So we're looking for the net torque, right? So summation of all these torques. So torque 1 plus torque 2 plus torque 3. Okay, so when we do this, we have sort of, it's a little different here because we have 2 rings, or we have like 2 different radiuses that we're working with here. So you can think of this center one as, or you can think of this as like a gear on a bicycle, right? So this is the smaller gear. I'll give you more power when you're pedaling on it, and then this is the larger gear, and you'll want to use that for like uphill and all that crap. So so yeah, let's do this. So the first force gives us the first torque. It is being pushed at an angle to, so it's not tangent to the circle that is pushing it. Okay, so now we have to find out essentially how much force is actually being applied on this wheel, right? So essentially, we want to find the tangent force to this wheel. So if we can break this into like its x and y components, right? So that's y, that's the x. That force vector is at a 30-degree angle to its x component. So if we just do our like cosine rules, then we should be able to get our answer, right? So the torque for the first force is, it's going clockwise, right? So it's going to be negative 400 times cosine of 30 times the distance, so, or the radius, so times 3. Okay, so that's for the first torque. That's the first torque right there. Second torque is on the inner circle, right? So it just has a different radius. So it's going also in the negative direction, right? Clockwise. So 300 times, what is it? 1? Yeah, 1. Okay, cool. And then the third torque, right? The third force is going in the positive direction. So 500 newtons of force, and it is 3 meters away. Okay, and when you add all those up, you get 160.77 Newton meters. So what direction is this wheel turning? It is turning in the counterclockwise direction, right? So counterclockwise. That's how they abbreviate it, I think. Yes, because we define that as a positive direction, and we have a positive torque. Cool. Zoom is not complying with me today. There we go. Okay, last one, number 5. So the positions of masses, those, right, are at those coordinates respectively. Determine the position of the center of mass of the system. Okay, so this is like, these problems actually aren't that bad if you break it down. So let's draw a sort of picture of what's going on. So we got our coordinate system, our axes. Okay, so we got, let's look at the first one. So we have 4 kilogram mass at 0, 0. Perfect. 4 kilogram mass right here, right? So this is 4 kilograms. And we have 6 kilogram mass at 4, 0. So 1, 2, 3, 4. Let's do it there. 6 kilograms. Okay, and then we have a 7 kilogram mass at 0, 5. So 5 on the y-axis. Oh shoot, 1, 2, 3, 4, 5. Okay, so there. So 7 kilograms. All right, so now we have to find the center of mass between these 3 masses. So really all you have to do here is dissect it into its x's. You sort of just average the x's and average the y components, and then you do, that'll give you where it is, right? So if we break it down, so the x components, essentially what it's going to be is x equals mass 1 and its x coordinate plus mass 2 and its x coordinate for mass 2, and then divided by all the masses, right? So mass 1 plus mass 2. That's the general equation. So when we do it and we break up the x coordinates for all these ones, so the x coordinate for 4 kilograms is what? It is 0. Okay, cool. So plus the x coordinate for the 7 kilogram is 0. Yes. And then 6 is 4. Divided by, and then when you add up all these masses, it should be 17 kilograms. Right. And then, so that gives us our x coordinate when you do all the math. It's 1.41. Okay. So now let's do the y coordinates. It's pretty similar, just averaging all the coordinates. So the y coordinates for 4 is 0. The y coordinates for 7 is 5, right? And 6 is 0. And then 17, right? So then the y coordinate is 2.06. 06. Cool, we got our x and y coordinates. So where is our center of mass? Well, it's at 1.4. And then we trace that up to 2.6 or 2.06. So it's around here. Yeah, it's around there. Cool. Yeah, kind of, it's kind of symmetrical in all these. Ideally, it would probably be more towards the 7 kilogram mass, right? Because the more mass you have, the more it's going to be tipped that way, the center of the mass, if you can imagine that. So yeah, if you have any questions on this stuff, go ahead and comment, and please sign in if you haven't done that already. Cool.